Here's an example of a circuit in the frequency domain. We've got, as simple as possible, 1 volt peak, 1 volt RMS peak, voltage source going here, AC voltage source, and it's going through what you'd expect to find in a typical industry, which is a largely resistive but partly inductive load. So if we were to draw this load of 0.81 real ohms with 0.59 imaginary ohms in the complex plane, we'd get this impedance triangle. So this dot up here corresponds to the load of this resistive inductor combination. And the way that I've drawn it, we can change what the magnitude is of that load. We can also change the angle of that load using this slider down here. So if we change our angle to 0 degrees, then our voltage and our currents will be exactly in phase. Let me draw those two. You can kind of, it's hard to see, but there's blue and there's green, and these guys are right on top of each other, which is why you can't see the difference. And so we've got a purely resistive load. Our power triangle is perfectly to the right. This little dot here is our S phasor. And when we take a look now at these different components, let's take a look at our power. We've already talked about how our voltage times our current is, I'm going to make this magnitude not quite 1, so you can clearly see the difference between voltage and current. Now, when these are both positive, our instantaneous power is positive. When these are both negative, two negatives together are a positive number. But when they're 0, our instantaneous power is 0. So so this is what it looks like versus time. Our average power is going to be the average of our red waveform, which I would have thought would have been in the middle here. I'm going to have to think about why that's not true. But we're going to have no reactive power, and our complex power, which is our apparent power, is going to be right on top of our real power, because there is no reactive power component. Now watch what happens as we make our power factor lagging. So we've got this non-zero inductor going on over here. If we make it just slightly, if we just make it slightly inductive, I'm going to make it a little bit more so it's clear how inductive it is. Okay, now when we multiply these guys, you'll see that our power factor definitely dips negative. If we had less of an imaginary component, less of an inductive component, it would be more positive everywhere until finally it's purely positive. But as we make it more and more inductive, it dips more and more into this area where we're delivering power back into our power lines. Now you can see our average power is dipping. You can see now our reactive power is considerable. So when we had a purely real, we have no reactive power. As we increase our inductive component more and more, the reactive power increases until finally at 45 degrees, when the resistive and the inductive components are equal, the real power and the reactive power are the same. And as we continue to grow it, our reactive power increases until finally we're looking at all reactive power. Our real power, our instantaneous power, is being shuttled back and forth, and our average power is 0. If you do the opposite, if you go into a capacitive system, now we've got now for our capacitive system, now our current is leading. Our current here in green is leading our voltage. It hits its peak before voltage. So now we're in a leading power factor. We've got our a capacitive system. Our power, once again, will slightly dip negative. If we were to make this more and more capacitive, our instantaneous power would dip negative more and more as the capacitor is delivering system back into our power lines. Our real power is positive. We have a reactive power because it's capacitive, it's negative, and as we make it more and more capacitive, it's going to get more and more negative. And that's our magnitude of our resulting power, which you'll notice the magnitude of S doesn't change as we alternate our real versus our imaginary components. That apparent power in turquoise is staying the same. And that apparent power is really the total amount of power that the power company is losing. That's a lot of material. Any questions for me on this?